Hello, my name is Qianjun. I'm a postdoc at University College London, and today I'll be talking about calibrating high-redshift tiles with Lyman-Alpha forests. I'll start by talking about photometric redshift calibration, and then provide more detail about clustering redshift methods. Photometric redshifts are widely used in cosmological surveys. These are coming from photometric surveys, where you measure fluxes of each galaxy in a few different photometry bands and infer their redshifts. You can obtain point estimate of the photometric redshifts or ensemble distribution of your galaxy samples, such as the source and lens tomographic bins in the DESI S3 analysis. Because you don't have the full galaxy spectrum, photometric redshifts often come with a wide uncertainty range, as well as a bias. Despite these complications, these informations are passed down to your cosmology pipeline in order to obtain a parameter estimation for your cosmology. For stage 4 surveys, systematics needs to be controlled to sub-percent level in order not to bias the results, and photometric redshifts is one of the main sources of systematics here. Clustering redshifts provides a photometry-independent calibration for your redshift distribution. The idea is that galaxies are tracers of larger structure, so they themselves cluster. Imagine you have an unknown galaxy sample where you want to know the redshift distribution of, as shown in this black-green box on the screen. What you can do is you can compile a reference sample that are concentrated at certain redshifts. These samples are typically spectroscopic galaxies that have very fine redshift resolution. Then you can imagine that if you have redshift overlap in the two samples, then you're going to get some clustering signal. On the other hand, if they don't overlap, then you will get no signal. And you can see that the cross-correlation amplitude must contain some information about the unknown redshift distribution. To give it a little bit more detail, the conventional clustering redshift methods works as follows. We measure the pair counts between the reference sample and the unknown sample as a function of the angular separation on the sky. Now, what gives the clustering signal is essentially the 3D isotropic correlation function of the large structure. This function is scales with the 3D separation of the pair, which can be written as the angular scales of the pair as well as their redshifts. To illustrate this effect a bit more, as well as simplify some calculations, I'm going to introduce some approximations that are common in conventional clustering redshift methods. One of those is the Limber approximation, where you assume that only pairs within the overlap of the n of z's, so here illustrated by these green bands on the screen, contribute to the correlation signal. This is true if you are measuring this on a very small angular size, such that the pairs separated by large 3D scale at the same theta, so that means they are separated well in redshifts, does not contribute to the signal. This is also valid if you have very wide top hat bins, so that missing pairs at the edges does not matter. The other approximation says that your bins can't be too wide, so it has to be thin enough so that the bias of the reference and the unknown sample do not evolve significantly over this range. And you can write your unknown redshift distribution as some average centered at the center of the bin. If you assume these assumptions and you work out the math, you will find that the cross-correlation amplitude is directly proportional to the unknown redshift distribution. What's more, you can even use the information from the autocorrelations of the unknown and the reference sample in these thin top hat bins. If you measure that as well, then you can write down the N of z of the unknown sample directly as a ratio of the 3 correlation functions. Of course, in reality, you won't be able to really measure the unknown autocorrelation, but you can model it in some way and assume a bias evolution of the unknown sample. Of course, this comes with complication and uncertainties, but despite this complexity, you can work pretty well with the clustering Z method for many of the stage 3 surveys. Here I'm showing an example from the Kids legacy analysis where the clustering Z measurements are shown in black. The blue line, which is overlapping almost with the red line, is the N of Z coming from photometry alone. And the red curve on top is the combination of the two. And you can see that in the top panel, the two agree very well, which means that you've done a very good job of calibrating your redshift distribution. On the bottom, on the other hand, you can see that clustering Z is able to correct any bias that you have in your photometry-only estimation. This is a very useful method, but there is a problem in the sense that you need a calibration sample to perform this analysis, and typically at high redshift they run out. This is an example of the HSC Year 3 analysis, and you can see that the top 2 tomographic bins are only partially or completely not covered by any spectroscopic sample. As a result, their redshift distribution uncertainties propagated to cosmology is much, much larger than the 2 lower redshift bins, which are precisely determined with the calibration. This means that their cosmological constraints are then heavily degraded in these top 2 bins. So it would be really great if we have some clustering redshift calibration samples at high redshift that allow us to pin down also the uncertainties for these high redshift bins. So there comes Lyman-Alpha forests. Lyman-Alpha forests are absorption lines in the quasar spectrum arising from the Lyman-Alpha electron transition of the neutron hydrogen. The absorbers are typically intergalactic gas along the line of sight of the quasar. They can be diffuse gas living in the intergalactic median or gas overdensities arising from such as big galaxy clusters. These are both tracers of larger structure with different biases. What's really great about this is that the redshift of these absorptions can be very precisely determined. So essentially, Lyman-Alpha forest maps out the 3D structure of the underlying distribution at high redshifts. One difficulty in this method is continuum fitting. This refers to the process to turn the observed flux into our large structure tracer delta F. To do this, you need to know the quasar continuum of the unabsorbed spectrum as well as the mean transmitted flux. This is illustrated at the bottom plot, where this continuum is shown in the blue solid lines. And you can see that determining precisely this continuum is key to getting your fluctuation amplitudes correct. It turns out that this affects the cross-correlation amplitude for our clustering measurement a lot. What's showing in these 4 panels are delta F galaxy cross-correlations measured as a function of redshift and at different angular scales. The first panel on the left shows you the perfect case in simulation where you know the ground truth of your delta F. And the second panel shows the fact that you now add noise to your quasar spectrum, but you normalize it with a known true continuum. This is the best case scenario we could do in reality. Now the last two panels shows two different continuum fitting methods. Picca is a method that's widely adopted in Lyman-Alpha forest community. It's a template fitting method that when you do the fitting, you kind of distort the delta F field. This is a known effect that you can correct for, and it doesn't really impact the 3D correlation function. However, you can see that when you apply this to the angular correlation function, it washes out your signal almost completely. The last panel shows a recently proposed machine learning method, LyCAN, which predicts the continuum based on a training sample as well as the red side of the Lyman-Alpha forests. You can see that this method is performing very well and almost reproduce the best case scenario where we know the true continuum. So these plots shows really that continuum fitting is a key to get the cross-correlation signal. But this is not the full story. In order to use Lyman-Alpha forest to calibrate high redshift tails, we really need to understand some complications at high redshifts. These complications arise from the fact that given a fixed redshift bin width, the co-moving width decreases at a higher redshift, so your top hat beam becomes thinner at higher redshifts. This means that what we have seen, all these assumptions are made for low redshift, does not necessarily hold for high redshift at redshift around 2.5. And one of those assumptions is the limbo approximation, which we said we need a wide enough bin. This does not hold anymore. The other effect we haven't talked about is redshift space distortion. This effect is very large for Lyman-Alpha forest, and even for galaxies, they cannot be ignored. What is RSD? This effect refers to the fact that the observed redshift of a galaxy does not only encode the Hubble flow, but also peculiar velocity of each galaxy. Peculiar velocities arise from the fact that galaxies are drawn by the gravitational potential of the underlying large-scale structure. On very large scales, which is the scales that we concern ourselves here, this effect is called the quasar effect, and it refers to the fact that there is a coherent inflow of galaxies towards the center of a cluster, say. The level of distortion given by this effect is governed by this beta parameter, which is the growth rate, which is given by the growth rate of large-scale structure as well as the bias of the tracer. The effect is such that this 3D isotropic correlation function now becomes squashed along the line of sight. How big is the RSD effect at high redshift? Well, these three panels shows you the correlation functions with or without RSD as a function of angular scales and mean redshift of the top hat bin with a thin bin width. For the galaxy and Lyman-Alpha autocorrelations, these are correlations measured in these thin bins, whereas the cross-correlation refers to the fact that Lyman-Alpha forests are in thin bins, whereas the galaxies have a wide redshift distribution. So these are the three functions we use for our N of Z estimator, as we mentioned earlier. Now you can see that RSD does not affect the cross-correlation that much because of the wide kernel, but it has a huge impact on the autocorrelations. This effect is redshift dependent as well as angular scale dependent. And in the case of Lyman-Alpha autocorrelation, you can get a factor of as big as 10 times. Now, coming back to our N of Z estimator, if we put these three functions together to obtain this N of Z, do we get back to the truth? The short answer is no. On the right-hand side, I'm showing you a simulation case where the true unknown redshift distribution is shown in orange And the measurements from this ratio of the cross and autocorrelations are shown in the black data points. You can see that there is not only an amplitude mismatch, but also there's a tilt introduced to the shape of the N of Z. And if you account everything correctly, you get the blue line, which then you can explain your results. But it does not overlap with the truth. This really says that we need to be very careful when we implement this method and interpret our results. Either you would want to measure this at very, very small angular scales, or you will have to fit the cross-correlation directly. Despite these complications, it is still a very promising method to calibrate the high redshift tails of the stage 4 photometric surveys. This is because these surveys will be much deeper compared to any surveys we have at the moment. And so a large proportion of galaxies will need cross-correlation measurements at high redshifts. So here I show the scenario for the LSST year 10 datasets. The orange curve shows you the highest source spin in the weak lensing analysis. And you can see about a third of the sample lives beyond redshift 2, where you will find very hard conventional spectroscopic surveys to cross-correlate with. But Lyman-Alpha will give you a very decent coverage. Another example is Lyman break galaxies, which are found by U-band dropouts. These galaxies peak at about redshift 3, and again, it will be hard to find any spectroscopic galaxies to calibrate them with, but Lyman-Alpha will provide a very good reference sample. So in summary, I hope I have convinced you that it is very important to calibrate photometric redshift distribution, and cross-correlation redshifts is a powerful way to do that. We can use Lyman-Alpha forwards to do this at very high redshifts. However, caution needs to be taken in terms of interpreting the results or conducting the measurements. Perhaps instead of using this ratio that we constructed, one will have to fit the full correlation function. Thank you.